I like to use a simple example to show you the importance of data structures. Yeah. All right. C.1, search unordered arrays. Yeah. So this is a simple problem. Yeah. Our computing problem, number 3, search an unordered array. Yeah. The question, given an unordered array, we use this representation. Yeah. The data size is n. Okay, yeah. And a search key k. Search key. Yeah. Here, the search key, you can understand in this way. Yeah. So the key value should be one of the values in the array elements, should match one, not that, should, could, because there is a possibility there is no match. Later we will have that case. Not should, could match one of the elements in the array. All right. Now, our goal to find an index I such that k equals A of I. There is a possibility this I cannot be found. That case could happen. So, all right. So this question, very simple. I believe everyone in this class, you can solve this easily. Search. You just compare the search key k with all the elements. So you run a for loop from beginning to end, compare one after another. When you find a match, you get out of the for loop, right? So that's basically what you need to do. But here we like to consider a few basic concepts in this simple question. First, the problem type, basic problem type. We have several basic problem types in this class. This gives us the first one in this type. So which type? Search type. Search type. And the data structure used here, array. Also, basic type, array. Later, we will learn some more advanced data structures. But most of the time, we use array data structure. All right. And here, I give you the reference in the textbook, section 2.1. All right. So the question, why the data structures are important in algorithm design. Here, I like to point out important usage of the data structures. Make our data well organized. That's the important way we use the data structures. Organize our data with some special properties. We can choose organizing the data or do not organize the data. We have options. If you like to organize your data, you need to pay some cost. You need to, pay some effort to organize the data. But after you organize the data, your data should have some desired properties so you can enjoy the good properties, the good results. Yeah. So later we have another example, so I can show you, to pay some cost for preparation, for data preparation, you can get better results. You have a chance to get better results. Yeah. Data organization in our second example, if you recall the chessboard question, counting number of squares in the chessboard, we organize our data for different data sizes, right? 1 by 1, 2 by 2, different data sizes. That's a simple way to organize data. Yeah. Later, we will have many different ways to organize our data. So here, I just, at a high level, pointed it out. To organize the data in the preparation step, it could be very useful. Okay? All right. Yeah. But for this question, actually, we do not pay any effort to organize our data. We just take the data given. Then we solve the problem immediately. We do not organize the data. Yeah. But all right. Through data structures, so that our algorithms can take advantage of the structures. Now, here I like to point it out a common way that people do to organize the data. So that is sorting. Sorting. Yeah. Given unordered data, so we do not arrange the data in ascending order, in any order. Yeah. But what do you mean to organize data? Here, I give you one commonly used method to organize data. So that is sorting. Sorting. Okay? You need to pay quite a bit cost. Yeah, because sorting is pretty expensive. Yeah. But after you pay that much cost on sorting, then you enjoy the result with the property data is ordered in ascending order. The data is organized in ascending order. Then your algorithm, when you design your algorithm, you can enjoy the ordered data property. How about that? Then your algorithm could run much faster on ordered data. So that is one typical way that people do in many of the computing problems. All right. Yeah. Yeah. But we will see that example later. Okay. Yeah. All right. So here, let's solve this problem quickly. Yeah. Because this is a very simple problem. Yeah. Basic operation comparison. Yeah. And when we do comparison, each step, we have several different results: equal, not equal, greater than, less than. Yeah. But when we do comparison, we start from the first element in the array with index I equals 0. Okay. So then in every iteration, we compare k with the current element, a of I. If they are equal, then we return index I, and we can terminate the program, because that's all we need to do. Yeah. But if k is not equal to a of I, then we need to move to the next iteration. Compare k and a of I plus 1 and repeat, But your program has to terminate at the end. And after you compare k with all the elements in the array, yeah, so that means your I moves to the last index n minus 1. After that, you do not have a match, no match. Then you return -1. Yeah. So your function, the return of value -1, because it's not a valid index number. A valid index number cannot be negative. So you use -1 to tell, the programmer or user, there is no match. That's possible. Yeah. So this logic, using this simple logic, you complete the whole solution. Yeah. So that is the whole solution. Okay. Yeah. All right. So after that, we want to have some discussion. Yeah. Yeah. So first, this algorithm, very simple, but there is a name for it. One we call a sequential search, but also another name, commonly used name, linear search. So sequential search or linear search. Yeah. And it is a basic, our first search algorithm. Later, we will learn another important search algorithm, binary search. Okay, yeah. After that, we learn another advanced search algorithm. Yeah. So we won't have many different search algorithms. Yeah. But this is the first one. Yeah. All right. Here, this question, how do we measure its performance? We know its basic operation is comparison. In this question, we do not do addition, we do not do multiplication, as in our polynomial evaluation. So our basic operation is comparison. So how do we measure its performance? Naturally, you can see we use the number of comparisons. How many comparisons do we need to find the given key? That's the measure, number of comparisons, that's the measure, okay? Yeah. But there is another question. Yeah. If you use the number of comparisons, then you have the chance, sometimes when you are very lucky, when you do the first comparison, you find your key to be searched in the first comparison. So when you are very lucky, okay? But many times you may not be that lucky. Yeah. So you need to do comparison with many elements in the array. And you have the chance, you need to compare your search key with all the elements in the array. So here you have the best case, you have the worst case. Okay? Yeah, right. Yeah. Oh, yeah, case one, yeah, best case and the worst case. Yeah. But when we talk about measuring the performance, which one, which case should we use? Should we use the best case or the worst case? Yeah, if you use the worst case, all right, so let's think about let's think about if you use the worst case. For this particular question, our worst case, we need to use n comparisons, right? Because we need to compare the search key with all the elements in the array. That's the worst case. Okay, so let's think about if you use the worst case, that means you give people impressions that we need to use n comparisons. Is it the best way to describe the search performance? Okay, do you think that's the best way to describe the search performance? Okay, yeah. All right, let me give you a little more background information so you can think about if this is the best way for the search performance. Give a range. Yeah, all right. So here we talk about the number of comparisons. Okay, yeah. So you want to have a range for the values, of the array elements, that range. You want to have that? Yeah. But if we look at the comparisons, that range may not have any impact, right? Think about that. Yeah. If the range is between 0 to 100 or 0 to 1,000, is there any difference? You still need to do the same number of comparisons, right? Yeah. Think about that. Yeah. All right. So here, let me go back to what is the fair measure for this algorithm? I want to address this question first. Yeah. The fair measure. All right. Let me give you a little more background because the search operation, think about everyone may do search operations every day, right? When you search, you type keyword in a search engine. That's the search operation. Okay, you type a keyword. Your keyword, that's the search key. Here, our K. Yeah. Although in this question, we use some number for K, but when you type a word, can we convert it to a number easily? Yes. If we like, we can convert any word to some integer value easily, right? Yeah. So it's not a big difference. Or we do not need to do conversion. We just compare a word with array elements, and we assume our array elements also take the string values, string array. Yeah, we can do that comparison also. Yeah. So think about that. So when you type a keyword in the search bar of a search engine, okay, then the search engine will, use that keyword so then to do the search in a pool of data. A pool of data, right? Yeah. Think about that, pool of data. Yeah. Here, our array, it's just a model of the pool of the data, right? Yeah. In the real world, that pool could be huge, a huge pool. Yeah. Yeah, but here we want to simplify that pool. So we use an array to model that big pool data. Okay. Then you have a chance, the first element in the array, you hit it, then only one comparison. After that, you may have 2 comparison cases. Then you have 3 comparison cases, and so on. And the last one, you have n comparison case. The question, which case do you feel is the best to describe the overall measure? This question, overall measure. Okay? Yeah, because sometimes you hit 1, sometimes you hit 10, sometimes you hit 100. There are so many people in the world do the search operations every day. Some people fall into, so yeah, here the range probably. Yeah, so here I got your, genetic and medicine. You talk. Oh yeah, genetic first, the range. Some people, the number comparison may fall in a range between 0 to 10. Some people, the number of comparison may fall into the range between 10 and 20, and so on. Okay, if you're thinking that way, so then you can talk about range. Yeah, but here, medicine gives a good answer, average. Average. Yeah, that's the best way to describe the overall performance. You need to take average. People do millions of search operations every day. Okay? Yeah. So the number of comparisons are distributed from small number, then large number. Yeah. But at the end, you need to consider the average number of comparisons. So we call it average case efficiency. So we have the best case, we have the worst case. Yeah, but here we need to run this algorithm so many times, millions of times. So which measure is the closest description of the overall efficiency? The average case efficiency. Yeah. So you may ask how to define average case, right? For the best case, you can understand easily. For the worst case, you can also understand easily. But for the average case, you know how to take average of n numbers, right? When you have n numbers. Yeah. So here, let me write our first understanding of the average. When you have n numbers, 1 plus 2 plus 3 plus n. Yeah. This could be our first way to define the average, right? Yeah. This could be the most straightforward way we can use to describe the average number of comparisons, right? Yeah. But for this search problem here, if you use this expression, you ignore several important factors. You ignore several important factors. So you have to consider some important factors. Yeah, so in the next slide, we need to consider another important factor in order to represent this average number in an accurate way. This version is not that accurate. Most of the time, it's not that accurate. Yeah. So we have to consider a few more factors to get a much better, more accurate expression. Okay, all right. Yeah. So let's consider the operation. We need to count the number of comparisons. We need to study all the possible cases. Then we can look at the average. We need to understand the details of all the cases first. Yeah. So let's do a chart here. Yeah. So let's list all the cases here, but you can see there is another important case, no match case. We also consider here. Yeah. In the previous slide, when I write the average case formula, I didn't consider no match case, right? If you go back to look at that formula, we didn't factor in the no match case. You ignore that no match case. That's one of the reasons that version is not accurate. Yeah, all right. So here we consider that no match case. No. A of 0, 1 comparison, A of 1, 2 comparisons, and so on. A of n minus 1, we need n comparisons, and for no match case, also n comparisons. So now, how to take the average? So here you can see we add, yeah, in our previous slide, we ignored the last case, no match case. Now, we get it back. After we get this no match case back, let's look at the average number of comparisons. Okay, yeah. Now, let me write one formula here, and you tell me if it is correct or not. Okay, yeah, because here we have n minus 1 cases, not n cases. Oh, sorry, n plus 1 cases. No match, so we add one more, n plus 1 cases. Now we should do average for these n plus 1 numbers, right? Yeah. So let me write this formula. Yeah. Yeah, the space is a little small. 1 plus 2 plus ... plus n, the first n case, then the last case also n, divided by n plus 1. How about this expression? Tell me, is this a good average number for this algorithm after we factor in no match case in this way? Do you think this is an accurate average number of comparisons for the search algorithm? Think about this formula. It looks a little better than the previous one, but is there something missing here? Is there something missing here? Okay. Anything important not considered in this formula? Okay. Yeah. Nobody answer. Yeah. But actually, there is another important factor not considered. Okay. Yeah. Here, when you take averaging this way, you assume each case occurs with the same probability, right? Case 1, case 2, and then no match case occurs with the same probability as any of the first n cases. That's usually not right, right? We cannot assume that. That assumption is incorrect most of the time in the real world applications. Okay, so here, the important factor we didn't consider, that is the probability for the no match case. We need that probability number. That number is important. So, but that data, people need to get that data in some way. People can use the history, history, statistics in history data to estimate that probability, but you need to find it first. Before you calculate the average number of comparisons, you need to find that probability number. Okay, yeah. So here we have best case, worst case. Yeah, but the worst case, you need to consider two subcases, right? Two subcases, both n number of comparisons, but they may have different probabilities. Yeah. All right. Yeah, so here, right? So we passed this step. We know we should use the, average case efficiency. But the question is how to represent the average case efficiency in an accurate way. That's the question we need to answer at this point. Yeah. So we need to make some assumptions, make some reasonable assumptions here. That probability, mainly regarding the probability for individual cases. Yeah. All right, so let's do that probability, okay? Assumption. Assume that for the first n cases, yeah, so our first assumption, assume that these n cases have the same probability. That's okay. Yeah. Yeah. That's the, in general, we use that assumption in our real world applications for the first n cases. Okay. Yeah. Then we also need to make assumption for that no match case, probability for the index case. So that's the matching case, right? Index. Yeah. So you can find a matching element, a matching array element. So matching case, the index case with probability P. So that means this P should be given at the beginning. Okay? Yeah. Yeah. How to get that from the history data? We do statistics from the history data. So we estimate that P. Okay? Yeah. After we get that P, that means with this P, little p percentage of chance, the given key K appears in this array. Okay? Then for the no match case, -1 case, its probability is 1 minus P. Okay. After these two assumptions, now we can write our average number of comparisons in an accurate way this time. Yeah. The best description we can find for the average case efficiency. Okay? Yeah. So let's do our final formula, final version of the average case formula. Okay. Yeah.